So, hello and welcome to this webinar on meeting the challenge of big data with big memory. My name is Mike Croft. I'm part of the Managed Services team here at C2B2. And this is just one in quite a few webinars that we've done as a company. So please do follow us on YouTube, Twitter, and on our blog, and you'll get more details of the sort of things that we do semi-regularly. So you'll need to subscribe to get updates. And I've got a slide about that at the end. So the agenda for today then, first to kick off, I think the best thing is to define what big data actually is. It does seem like it's one of those buzzwords that does get thrown around a lot, but it's important to properly define so that we all know what we're talking about. So first we're going to look at definitions, and then we're going to look at what makes big data so difficult, just having more of something, how can that be more of a challenge? Then we're going to look at how can we solve these problems. We're going to look at existing solutions, see what people have come up with to address these sorts of problems that have come up in a more generic way. Then we're going to move on to big memory, which is Terracotta's solution to the problem of big data. And we're going to look at performance, scalability, and high availability, which are three areas that are very crucial to think about when you're talking about big data. So firstly, definition then. What is big data? Well, I went on the internet, as is the first port of call, to get a proper, good, solid definition of big data. So the internet definition, thank you Wikipedia, is in information technology, big data is a collection of data sets so large and complex that it becomes difficult to process using on-hand database management tools or traditional data processing applications. So what that means is that big data is so much larger than we've been used to in the past, and so much more difficult to process in such volumes that the approaches that we've used in the past, such as traditional database management, is just not going to cut it. It's not good enough, and it won't work. Just following on from that definition, Wikipedia says the trend to larger data sets is due to the additional information derivable from analysis of a single large set of related data, as compared to separate smaller sets with the same total amount of data, allowing correlations to be found to spot business trends, determine quality of research, prevent diseases, link legal citations, combat crime, and even determine real-time roadway traffic conditions. So this is not only something that's incredibly difficult to do with traditional means, there is a huge amount of value to it. Okay, and one final point to make is that it is not fast data. There is some overlap here, as we'll see a bit later on. There's a lot of these terms have a bit of overlap. They're not rigidly defined, but fast data is something a little different. In scenarios where you'll find one of them, like in scenarios where you'll find big data, you will often find there's also fast data. But big data refers solely to the volume of data. There's just a lot of it, whereas fast data is much more concerned with real-time event processing and data streams. So just a bit more of a practical, tangible list of things. We've heard about it in an abstract way. In a more practical sense, big data could be thought of as the Internet of Things. This is a big thing that businesses are pushing. I know IBM certainly are pushing it, Oracle are as well. You may also have heard it referred to as M2M, or pervasive computing, which is M2M being machine to machine. This is where anything can talk to anything. It's the idea that everyday objects can be users of the internet. So for instance, your fridge can connect to your local supermarket and order milk when you run out. These devices have got sensors in them that can tell you things. Just by way of a real-world example, there's the house that tweets. This is the house of a man called Andy Stanford Clark, who works for IBM, and he's hooked up a huge array of sensors to his house, and there's an example of one of the tweets that his house produces. Someone left a window open. So if he's got a lot of these different sensors around just to tell him things, alert him to things, he's even used it to automate various different things in his house. So he can now control lights and turn things on and off based on this data that he's getting. You can think that that's just one household. Now I've done a bit of research, and there are about 22 million households in just the UK alone. So with 50 sensors per household as an average, that creates a huge amount of data. And that's only considering home usage. That's not even considering the usages of business and office users. Another example is Windermere Real Estate. Now this is a US real estate company who, in partnership with a company called INRIX in the USA, use anonymous GPS signals from nearly 100 million drivers in, I think, the Seattle area to help new home buyers determine their typical drive times to and from work from any prospective house that they want to buy. So they look up at a new house, and they've got all this massive data calculating what the drive time is at 8 o'clock in the morning from there to their place of work. So that's just a couple of practical uses of big data and why it can be useful, and how and the reasons why it's a good thing to try and address the complexities of it. So what does make it so complex? What are the problems involved? Firstly, you've collected your data. Now what? Once you've collected your data, you need to think about what you're going to do with it. Now there have been studies and reports, just one of which shows that 60% of, this was a US report, 60% of federal IT professionals say their agency is analyzing the data that they collect. So 40% aren't. They also said that 40% are using the data to make strategic decisions, so more than half aren't doing that. And less than half of agencies have enough data storage and access, and only 46% have the computational power needed. So these are quite interesting numbers, just to show how unprepared business seems to be at the moment to make use of all this data. For a start, collecting it, also analyzing it, and then making decisions. So the first thing is capacity is a big problem. Last year, IBM published some figures on this, saying that every day we create 2.5 quintillion bytes of data. That's over 2 exabytes every single day. That's not a week, it's not a year, that's 2 exabytes of data every day. And that's so much that 90% of all of the data in the world today, all of it, has been created in the last 2 years alone. Another problem is analysis. So when the infrastructure is in place to handle these vast amounts of data available, analysis of what data you want to collect is critical. You don't want to be collecting data that you don't need. And with such large volumes of data, even small percentages of unnecessarily collected data is going to incur a very large amount of waste. So once the appropriate data has been collected, that data itself then needs to be analyzed. But analysis on its own is going to be useless without decisions. The business intelligence gathered and learned from this data, whether it's about users, equipment, or environmental factors, all of it is going to be useless unless it's driving your strategy and your decision making as a business. So for these couple of problems, what do we need to consider? Well, first is going to be scalability to address your capacity problems. You need to think about, well, can we cope with not only the volume of data that we already need to collect, but can we also scale up to match potentially unpredictable growth demands? Performance. In many scenarios with big data, every second counts. Business intelligence and analytics drives the business value of this sort of infrastructure. So if you want to make, for example, time-dependent offers to certain market segments, perhaps people that have just arrived in a supermarket, then you need to give them enough time to claim the offers. So as soon as they walk through that supermarket door, they need to be receiving the text alert or the mobile app alert with the offer that you've generated for them. And if your system can't process enough data in time to generate these offers that are appropriate to that person, then they could end up being useless. They might get this notification as they've just reached the till to pay, in which case they're not going to make use of the offer. And finally, high availability is the other big one. A lot of use cases for big data in, for example, online social scenarios, think Facebook and Twitter, even sports news profiles. They require all these user profiles to be ready and available at all times of the day across the world. There's no window for downtime. Backups and failover procedures are going to be essential to provide the level of service that your end user is going to expect. So what solutions are available now? To start with, there's NoSQL. This is something that you might have heard of or come across before. Now NoSQL was really designed to replace a traditional database. This was the sort of aim of it originally, whether object or relational. It was optimized for write operations, which is traditionally not a great strength of databases, and flexibility, where in a traditional management system you've got rigid schemas that are going to add a bit more overhead. Next there's distributed caches. Now these usually I say complement a database, NoSQL or traditional, and they're optimized for volume and scalability. Now very often these are transactional, or they will have transactional capabilities like XA support, for instance. Next and finally on my list, there are data grids. Now data grids are very similar to distributed caches. They look very similar, work in a very similar way, but they're often optimized for distributed execution of code. So you want to have very many nodes and want to do massively parallel processing. Now that's in contrast to moving the data to where the processing will be done. So you've got one central place for the processing, you bring all the data to it. That's the other solution. Now data grids tend to focus on elasticity, which is often the telltale sign of a data grid, where you can add or remove new nodes very rapidly, very dynamically to react to changing requirements. So the main point of all this is make sure that you've got the right tool for the right job. Do you need something that's elastic? Do you need something that's transactional to support your database needs? Very often the deciding factor will come down to the type of data that you'll be working with. For instance, whether or not you know the format beforehand, so that you've got a pre-prepared schema, and what you want to do with it once you've got it. For example, you might want to do MapReduce style distributed computing. So now we've looked at generic solutions, let's move on to Terracotta's solution of BigMemory. The first thing to address is terminology. Now there are several things that we need to be aware of that Terracotta provide. First is cache. Now this is the popular open source Java cache that a lot of you are probably very familiar with. There is an enterprise version as well, which is a supported version from Terracotta, which is of course not free, but there is a free version of cache, which is quite widely used at the moment. Next there's BigMemory Go and BigMemory Max. Now these are probably best seen as two different flavors of BigMemory. And the easiest way to understand these three products and their relationship to each other is to see cache as the core, where BigMemory Go then extends that functionality by adding an off-heap storage layer. So you've got a cache and then you can store things off-heap. And then BigMemory Max will extend that again by adding a high availability layer with the Terracotta server array. So what all this means is BigMemory is a distributed cache. If you remember from the last slide, there was NoSQL, distributed caches, and data grids. BigMemory is a distributed cache. It's not a data grid or a NoSQL database, so although it does share some characteristics of both, it is optimized for different things. There is a significant amount of overlap between those three areas of NoSQL and data grids and distributed caches. Though they all did come about to solve different problems, the problems that they do solve aren't rigidly defined and they do overlap. So they have similar features, like for example key value stores. Very commonly they'll hold at least some data in memory, and a lot of them will be transactional. So in terms of benefits for BigMemory, what about performance? Well, this is a view of how Terracotta look at things, and their approach is to divide the available resource stack of your IT infrastructure into tiers and make sure they maximize the benefit of each tier. So this diagram shows each tier and its relative performance. And now obviously the memory that's directly available to the JVM, that top triangle there, is by far the fastest, and the speed there is measured in multiple millions of transactions per second. That's incredibly quick. Now right below that is off-heap in-memory storage, which is where BigMemory gets its name. So if both these top tiers are in memory, but on-heap is much faster than off-heap, why would you bother with off-heap storage at all? Well, if, as on this diagram, you've got 1 terabyte of RAM available, that would give you a 1 terabyte heap size if you make it all available to your JVM. Now that 1 terabyte would then all have to be managed by the garbage collector. Now as good as GC policies are with large heaps these days, we're getting a few new ones coming up to cope with very large heaps. There is a limit to how much data can be managed by the garbage collector without incurring massive pause times. Now you can optimize that and tune that for best performance, but depending on your scenario, you are going to reach a point where the benefits of adding more heap size are diminished by such large pause times that it makes it unfeasible. So that's why why Terracotta choose the BigMemory approach of storing things off-heap. Now one other way that companies have worked around this is that rather than having one massive 1 terabyte heap, they'll split the available memory into lots of manageably sized JVM heaps. So if you see here on the right, we've got the BigMemory solution of your application with 1 JVM and all the rest of the memory available to that application. On the left, there is an alternative solution of many JVMs or many applications, and then a lot of unused memory. Now, of course, the disadvantage here is that of wasted resources. So even if you do have multiple JVMs, rather than stacking your applications in the same JVM, if just 2% of each JVM that you assign is taken up with CPU overhead, GC overhead, and other internal processes, that 2% is then going to get scaled up and up and up with every additional JVM you add. So then, if that 2% is correct, then 2% of your entire system's resources are taken up with internal Java processes and not making money for you, rather than the BigMemory solution where you've just got 2% of that top 2 gigabytes, which is reserved for internal processes. So that's performance. What about high availability? Well, BigMemory Max provides high availability through the use of a server array. This is a product of Terracotta called the Terracotta Server Array. It's a very useful and easy to remember name. It is available to enterprise cache as well, but this is a diagram of BigMemory Max. So you do also get the off-heap storage with this. So each server has access to its own local off-heap memory as well as its own disk store, and you can see that in the bottom left of this image. servers are grouped together in stripes consisting of an active server and then a mirrored backup. It's very similar to a RAID 10 approach, really, where you've got mirrored stripes and then separate stripes, giving you more ability to scale out. Communication's done over TCP, and in previous versions this has used Terracotta's DSO technology, but that has been deprecated as of version 4.0, which is the latest version, in favor of a more efficient approach. So this is another example which takes things one step further and just shows how database reliance can be reduced with a greater reliance on Terracotta's distributed, highly available system. And the far right of this diagram shows how you really can take this to the nth degree with a virtualized or cloud-based infrastructure. And I must make the point at this stage that the database at the bottom there is not supposed to show the database size decreasing. It's supposed to just be changing relative to the amount of infrastructure that you've got available to BigMemory. So although the physical size of the database is the same, it's not as big relative to the rest of the infrastructure. So just having that capability of scaling is all very well, but how does it work in practice? What are the numbers like? You need to find out if there really is any benefit. So what about scalability? Well, this graph is taken from a recent performance white paper that Terracotta produced at the end of 2012. Now obviously with these performance investigations and white papers, it's really easy to focus on the numbers and just try and squeeze every last transaction per second you possibly can out of the setup and make the most of the machinery. But that's not what interests me in this graph. The thing that interests me is the massive increase in the size of the data set along with the relative stability of the throughput. So just to explain this graph a little bit, the numbers along the left-hand side, the y-axis, we've got the throughput in transactions per second, and along the bottom we've got data set size in gigabytes. So the test was run for each data set size. It was doubled each time, up to 1024, and then another 2 tests done after that. And you can see how even just through doubling the dataset size up to 1024, the throughput has stayed within 160 to 180,000 transactions per second, which is quite impressive to be honest. I was very surprised to see that. At 1.8 terabytes, the throughput is still above 90% of the throughput at 2 gigabytes. Okay. Now the thing to note about this is that we don't know what type of operations are going on here. All we can do is assume that they're probably just read operations, which would be quicker than writes. So let's look at another graph. Here it's showing similar numbers. The y-axis is the same, but the x-axis is very different. That's showing you write percentage. So now here we don't know the size of the dataset that's being used, but we do know how much of that dataset is dedicated to reads and writes. So it starts off being purely reads and goes up to 64% are writes. So over half of all the operations are write activities. And even with those increasing amounts, BigMemory does scale to over 80% of its maximum with 0% of writes. Now linear scaling is obviously the dream, but thanks to those pesky laws of thermodynamics, it's going to be impossible. So this sort of predictive scaling from BigMemory is really impressive, and it's a big reason that I think it's a good idea to consider BigMemory as a solution. If you want predictability, this is certainly something that I would recommend investigating very seriously. So just in summary and to wrap up, we've had a look at big data. We've looked at how it's challenging but also incredibly valuable at the same time. We've looked at big memory and Terracotta's solutions to those problems, and how it performs, scales, and how it can be highly available as well. Is there anything else? Well, yes. A couple of other things to mention is that there are free editions of BigMemory. Now, BigMemory Go, you'll remember, provides the off-heap storage capability of BigMemory. And there is a free license to use 32 gigabytes of off-heap storage. There are more details on Terracotta's website, which is terracotta.org. But if you are already using cache, I would certainly recommend you at least try out BigMemory Go. With 32 gigabytes for free, I think you will, in almost all circumstances, see some benefit to that. BigMemory Max, which is what provides your built-in high availability, gives you 8 gigabytes free per server. Okay, so in each stripe you get 2 servers, so that makes 16 gigabytes total, but obviously 8 gigabytes of that is going to be a mirrored backup. So that's practically speaking 8 gigabytes free. Also, there is Ingenious, which has come with the version 4 of BigMemory, and this is all very recent. It's a separate product, but it does provide data analysis in terms of event stream processing in memory data, as you can see on the diagram there, and that is very optimized towards fast data, which I mentioned at the beginning, which is when you need to react very quickly, grab the intelligence, grab the analysis, make decisions, and create offers for your users. So thank you for listening to the presentation. Do please follow us for more webinars. I will certainly be doing another webinar or a blog on Ingenious following Terracotta's process-driven forum, where they'll announce further details of Ingenious on June the 3rd. So following that, do stay tuned to our channels on YouTube, our blog on Facebook and LinkedIn, and I look forward to hearing you in the audience again. Thank you for listening.